All right. Good morning, good evening, good afternoon, and thank you for joining Going Meta, episode 9 of season 2. Today, the topic is structural patterns for ontology reconciliation. A little bit, like you said, has this little bit back to the roots of the initial Going Metas, where we talked a little bit more about semantics, ontologies, taxonomies, all that good content or the good these topics, versus I think in the last year or so we dived a little bit more into the AI side of things, but we also kept it steady along. I think these two topics really, they work together well. Knowledge graphs, ontologies plus AI is a great pairing. But today I think we'll keep AI a little bit more on the side, and we talk a little bit more about the ontology side, knowledge graphs, I guess, as a topic today.
That's right. I think it's kind of more foundational. I mean, it's we're going to be working on the on the scaffolding rather than on the more shiny side, which is the LLM. But it's it should be a good one. And well, first of all, hi everyone. It's great to be here. But I was mentioning before that I was having some network issues, so please at any time let me know if it goes bad in terms of screen sharing or sound or anything. So hopefully it won't be much of a hassle. But yeah, that's I was going to say that it's also a topic that we've touched on since we've been running these for years now. Alex, maybe people will not. We did touch on these subjects, probably sometime in 2023, more than 2 years ago. Anyway, the main reason to bring these, well, first of all, I was visiting one of our customers earlier this week, and this topic came up as an interesting one, like the idea of reconciling ontologies. And it's not miles away from LLMs. These days, LLMs can help in so many different ways and from so many different angles. So my plan is to inject the LLM component at the end. I don't know if today's session, but maybe in future ones. But again, the idea is, and that's what I put in the title. So ontologies, as we know, are graphs, and we've done a lot of work with them. And leveraging the structural elements in the ontologies, the shapes, and ontologies typically, we'll get back to that, classify things in taxonomy. So often you will find trees, and well, even not necessarily a tree. There's not always like it can be a generic graph, right, with the subclass of type of relationships. So being able to find alignments between different ontologies using these structural features is an interesting exercise, and that's where I want to focus the session today. And because I don't think we've dedicated too much time to it, because we've talked briefly here and there about one of our favorite labs projects, which is the RDF-lib Neo4j, which is the more sort of modern version of Semantics, which is Python, it's client-based. So I thought it would be an opportunity to combine the two, and that's the plan. I mean, long introduction, but that's the idea.
No, that's great. I think yeah, I don't remember. I mean, I remember that we talked about RDF-lib back when it was new, but we haven't talked about it recently. I also wanted to like you said, I think we might have touched a couple of these things in earlier episodes. It will definitely be new. So even if you have watched everything, then we will have something new for you. But coming back to what you said, we started a series now a long time ago almost, and I recently we had a very nice comment on our YouTube channel from somebody that's saying, I'm watching one video a day, and he's covering all the videos from the past, and now are trying to catch up with the most recent episodes. So even if you do that, then you'll see something new today. If you haven't done this and you just joined a couple of episodes ago, it's maybe a good thing to call back a couple of these topics we have touched in the past, which are still evolving and which are still with the new approaches that we are looking at, I think still make a lot of sense.
Totally. And we have the main contributors of the RDF-lib Neo4j library who would be very keen, if that's a topic of interest, who would be very keen to maybe join us for one of the sessions in the future to discuss what they're planning in terms of where they're taking that library and what additional features are they planning, or anything that people can come up.
Sounds interesting. If you also think that's interesting, give us a comment on the YouTube channel. Let us know if you want to hear more about RDF-lib, where it is, what it is. I guess we show a little bit today, but where it goes, I guess, and maybe if you have feature requests, and if you're a user of RDF-lib, also maybe a great interesting exchange. So yeah, if you're interested in that, let us know in the comments.
Good. Sounds great. So with that, probably I can start sharing my screen as we always do. Let me get started. So I'm going to share the whole.
Yeah, and while Jesus is getting this ready, as always, we try to keep it as interactive as possible. So if you have questions, comments, anything you'd like to see more, or if something you don't understand quite what we are showing today, then use the chat. I'm always looking out for your comments, your feedback. Generally, this is just a great repetition, I guess, from our side to you. So thank you very much for your continuous support. We really appreciate your comments, your views, your feedback on the show. It means a lot to us, and it is really great to see all these happy people. That gives us positive vibes coming back to the Going Meta series. So we really appreciate it. So thank you very much for that.
Perfect. So let's get started. Let me go on slideshow, and we've talked about the title. So we're picking a number of public ontologies. They happen to be in the life sciences space, because he's one of the richest, I have to say. And if you disagree with that, I'd love to hear that, because that's a question that we get very often. Like, hey, where is there a great catalog of ontologies? And I know, the usual suspects, the Obo Foundry for life sciences and pharma, but it's a bit more scattered in other industries. But if you have ideas, if you have ontologies that you use often, feel free to share with us, because we'd love to know about them. So right, so that's the title, and like I was saying before, today we're going to be mainly using the RDF-lib Neo4j package, which is one of our labs projects, and you have the link down here, so you can go to labs and you would see the whole collection. But this is kind of an evolution of the long-running Neo Semantics that was initially developed as a plugin, as we call it, which needs to be installed on the server side so that it extends the collection of functions and procedures that you have in Cypher. And because that's not always available, and sometimes you're using Aura, we thought that it would be a good idea to offer similar capabilities from a kind of a client side, right? And that's where RDF-lib Neo4j kind of was started. And now you have the documentation. This is a capture of what you will see if you go to this page. As all the labs projects, they are open source, so you would be able to go to and inspect all the internals in GitHub, and of course contribute. There's even a link to contributing, so the team is very keen to get you participating, deeper if that's your interest. And well, this is a Python implementation for those of you who haven't used it. So it's I guess Python these days is one of the most popular, if not the most popular language. So we thought that would be the natural place to start. And what that means is that it's as easy as do a pip install of RDF-lib Neo4j. That's what we're going to do. And we picked RDF-lib because you get from the name that we use. I mean, especially if you're familiar with it, of course. But RDF-lib is the most popular package for RDF manipulation in the Python space. So it has a number of ways to extend it, and that's exactly what we did. So the idea was to give you as a Python developer an experience that's as close as the one you have if you've used RDF-lib. The only thing you have to do is create what they call a store and bind it to your Neo4j database. In our case, we're going to be using Aura, but it can be your local instance. And by doing that, as you interact with your graphs in RDF-lib, your changes, your writes get persisted in Neo4j. And the logic that happens, because of course these are RDF graphs and Neo4j is a property graph, is the one that you already know and love, and is the one that we implemented in Semantics, which is a simple aggregation, right? So you just, if you think of the world in terms of property graphs, you know that the building blocks are nodes and relationships, and nodes can have properties and labels. Now, if you get the information in the form of triples, there's kind of a simple aggregation that you need to run. Is basically take all the triples with the same subject, and the subject will be a URI that uniquely identifies a node, and all the triples that have the same subject will become part of the same node. So we will create properties. We're going to see that in a minute, but that's basically what happens, the magic that happens behind the scenes, right? So that's pretty much it. And then when the triples connect to resources, that means they become relationships in the property graph in Neo4j. But all that happens transparently for you. So all you have to do is parse, query, and in our case, we're going to do kind of batch insertion. So we're going to take the whole ontology and put it into Neo, but it's going to be pretty straightforward, hopefully, as we're going to see in a minute. So that's the idea. Now, the examples that I'm going to use are three pretty common ones, and you might have seen this diagram before. So these are this is an example of a fragment of diseases from three different ontologies. Right? So the mesh is the medical subject heading. So it's an American ontology that's been around for quite a while. There's the disease ontology. And then Wikidata, which is a combination of many data sources, but it includes also, it has its own ontologies as well. So we're going to grab an extract. Again, we're not going to use the whole, except for the disease ontology, which we'll use in its entirety. For the other two, we're going to pick a fragment, and I'm going to take you step by step through the process of doing that. But once we have them, I mean, the idea is we're going to bring the three in the graph in Neo4j, and we're going to try to link them together. So some of them come already with cross references, and that's extremely useful because they're not complete. And I suppose, in the case of, for example, Wikidata or any others, I mean, there's people that are linking them and curating those links, but we'll see that it's a bit like what you see here. So sometimes you will have a perfect triangle, right? So it's kind of a flattened triangle, but you see a connection across all the three, and there's a perfect linkage. So that would be ideal because there's an unambiguous, connection. In some cases, you might be missing a leg, like here at the bottom, and we might, derived kind of predict what's the missing one. But in some other cases, it might be a bit less clear, and we're going to see some structural features. That's the whole point of today's session. So sometimes it's not as mirrored, as you can see. In some cases, there might be gaps, as in, something that's represented with 2 classes in one ontology has 5 classes in the other one. So it's maybe more granular. So how do we deal? At least how do we identify them? Because, again, dealing with them, these ontologies are human curated. So it is expert knowledge. So it's not something that we will, you can give suggestion in some cases, but it's something that you probably want to highlight, identify, and then have some humans making it evolve and align when necessary. So that's the idea. And without further ado, what I'm going to do now is go to my Python environment, which I hope you can see, and you're going to tell me that I probably need to make these a bit bigger.
Well, that's fine. I think it's all right.
Is it? Oh, perfect. Well,
yeah.
That's good. So, that's that's the first. I mean, we have three sources, and I'm going to. I mean, it's going to be a bit of replication in the code, especially on the Neo4j side. But it's hopefully pretty straightforward. Let me take you through the process. The first source that I'm going to use is Wikidata, right? And maybe it's worth showing you what this looks like. So as we've used in previous episodes, sometimes Wikidata offers a SPARQL an interface. I mean, there's a visual version, but there's an endpoint that we can query, and it contains a crazy amount of information. But in our case, I've worked on a very specific SPARQL query because RDF data is queried with SPARQL. And what I'm doing here is effectively what we're going to be doing in the code. So let's put a limit of 10 here just to make it quick. But this is a very particular type of query because it's a construct query. I'll talk a little bit about this construct part. But basically, what we're doing is we're looking for one of the nice things about Wikidata is that you pass the mouse over, it tells you what the relationships mean, because otherwise the numbers are very
yes.
But effectively, I mean, our starting point is we starting from here, from infectious disease, right? So that's the class, the category that we're going to get instances and subcategories from. So anything that is either a subclass of or an instance of an infectious disease, I'm interested. And this asterisk in SPARQL is similar to our asterisk in Cypher, right? It means go down these relationships as many times as you like. So I'm going to get all the classes that represents diseases that are subclasses of infectious, the notion of infectious disease. And for each one of them, I'm going to get some information like the label, which in RDF is how they call the name. The human readable is different from the labels in Neo4j, which are the types. But that's the disease name. That's what I call it like that. Because these are multilingual, I keep the English version, but you feel free to extend it and work with your own version of it in whatever language you prefer. And then there's some additional elements. So in some cases, we'll have a longer description, right? Not just the succinct and the short name, human readable name of the thing. There might be a description of it. Again, it's multilingual, so I keep the English version of it. And this is how we connect each disease to the parent. That's the one we saw that before, subclass. So I want to catch the pairs of child parent, so we can link them. And then here's the part that I was mentioning about. So sometimes in Wikidata, we have a cross-reference. This property is called a mesh descriptor. So it's not exactly the URI, but we can build it just by concatenating, because it has the mesh descriptor. And if we concatenate it with the prefix of the mesh URIs, we can get a proper URI. And I'm building it as part of this query. And then we have the same for the disease ontology ID. So it's already cross-referenced. We will not have for all of them, but we will have some, and that's a use.
Yeah, but that's good. Yeah.
So that's the extract that I'm getting from Wikidata. And then I'm instead of getting it in a tabular form, I could have done that. I could have taken it as a CSV and then create my own model. But because, if I serialize it as RDF, that's what I do with the construct. I just kind of rename things just to show that I can do it. It's not strictly necessary. So I'm kind of using my own namespace that I call Neo, but I could have called literally anything I wanted. And I use label, the description. I call this has parent to connect the parent, the same as my way of connecting my classes to the cross-reference ones. But again, this you could call it the way you want. The good thing is that if I put it as RDF like this, and it produces triples like the ones that you're getting here, we're going to be able to import them without me having to model anything. RDF lib Neo4j is going to do all the magic. So this query is just standard SPARQL. And back to my code. Here's what I'm going to be doing. So I define the endpoint. So that's where I'm running my query. So we've seen the visual interface, the UI, but there's the programmatic one that I'll be hitting with my code. And because I'm using RDF lib, I mean, they have the notion of a SPARQL store that I wrap with the URL, and all I have to do is create a graph out of it, and then I can query it. And this is the query that I just showed you. This is the big SPARQL query that will return the triples that I want. And when I run it, I'm going to run this query. This is going to produce a number of triples, SPO, that I'm going to iterate over. And these triples, I'm going to put them in a subgraph that I call the extract that I'm interested in. And that's all I need. Once I have these extract, I'm going to have to, I've just created a new Aura instance, so I'm going to have to update this. Bear with me, because the URI is slightly different. So let me replace it. The database is, I don't think we need that, because it's the default one is going to be Neo4j. The user is Neo4j. Neo4j, and the password, don't worry about this, because I'll destroy the instance after that, so not a problem. But these are my
link to Aura if you want to create your own instance.
Yeah, and well, these are my credentials, my authentication, and back to the to the RDF-lib Neo4j. What we do is we create this config where we basically tell RDF-lib that's where these are my authentication credentials, and this is a strategy that I want you to apply. You probably remember, if you followed us and you've heard us talk about Semantics, that you can take a number of strategies. You can ignore the names to make it more readable, not the long names, not the URIs of the resources, but the names of the schema elements. You can define how to deal with multi-valued properties. You can define how to deal with language tags. So there's a number of options. In this case, I'm just saying that ignore the names of the schema elements because it's going to be more readable, but that's just one of the options. And all I have to do is, okay, I create a new graph that represents my Aura database, backed by this store that I just created, and I tell it to parse the triples that I just extracted, the triples that I've extracted from the Wikidata and that are stored in my extract database, extract graph. So that's all. I pass them as turtle, and this should write to my database. So I'm going to run this code, and something very similar for the other two. But before I do that, and I'm going to show you the, did I mention the labs RDF, that's, hang on, let me, RDF lib Neo4j, is that the one? Yeah. Because we need to initialize. So if we go to getting started, there's one thing that I need to do, which is create this index on my database, and I have my Aura instance here. This index will just make sure that resources have a unique URI, and if we have it multiple times, they should be deduplicated. So that's all. I create this index. That's okay. Nothing more than that. And then I can go back to my code and hopefully without major issue, just run it and see what happens. So, oh, interesting. So what's going on? Config auth data. Do we missing the database key? So we maybe, I deleted it, but we maybe need that. So is the, let me do that. So there was how was it? There was this fill.
Yeah, maybe you need to
let's put it
the ID.
And the database ID, which should be Neo4j.
Or is this? Oh yeah, okay. Yeah.
I think so, because if the user is that,
no, yeah, right. Yep.
We'll find out.
Find out. Yeah.
Good. Okay, so it looks like it likes it now. So, well, that was quick. So, well, as you can see, it's also that it opens a connection to the store, then it's closed, and it's taking just a few seconds to load these 2,817 triples. So that was very quick. But we can now go to our database, and we see that we have a graph there, and we have the kind of things that we sort of define in our SPARQL query. So if I click on the has parent, that will give me portions of the taxonomy. Here we go. So you see how we have yeah, as I was saying before, it's not necessarily a tree. There might be sort of multiple has parent. A node can have multiple parents and not only one. But but the great thing is that we have the labels, the URIs that has been preserved. If I click on this, it would still be linked and would take me to the element in Wikidata, which is pretty cool.
Nice. Yeah.
So, but the important thing is that these are unique identifiers that are going to help me linking things together. Perfect. So we have the ontology, the first one of them, and what I'm going to do here is, in order to differentiate them nicely, I am going to that's something that I learned only a few days ago, and I'm so happy with it. So you can determine the order in which the styles are applied. So as you can see, because these things are resources, but they're also Wikidata diseases, it's applying this style because it's the first. But if I switch it and I put this one, it applies this style.
Okay. Yeah,
Which
that's nice.
is very cool, because here everything is going to be a resource, but I want for different types to have different styles, different colors. So in this case,
yeah, then we can see what comes from what.
Exactly. So that's I found that pretty cool and quite neat. So perfect. So we have this first portion of our ontology. The first thing that we're gonna find and we're gonna detect is that there are how would I call it? I call it sort of where is my code here? I think I have some cipher fragments. Do I have the shortcuts? No, I can find it. It's not a problem. So, but we find that the data that comes from Wikidata, it's a bit, I wouldn't call it, well, yeah, maybe a bit redundant. So in the sense that sometimes we have, let's call it a Wikidata disease that has a parent. Oops. So it will have a has parent. And let's call it P, that would be the parent. And then we have an alternative path that connects our disease. Also, it has parent, but with multiple steps. Let's say, for example, 2 or more. And let me find, this is, let's call it we can call it inferred or materialized. I'm going to explain in a minute. Return inferred limit. Let's give me just 3 of them. Good. Okay, let's see what this shows us. So what we're seeing is, let's see if I put all the arrows in the right way. Let's start with this one to the left. Okay, so we see that this dicrocoeliasis, right, has these as parent, and this has its own parent. So this effectively is the grandparent of this one. This is an ancestor. So this link here is redundant in the sense that, okay, I know this is your parent, this is your parent. I could have derived that. I mean, this is sort of an inferred relationship that we normally don't persist, right? So we don't need it. We can compute it, and it kind of, I wouldn't say pollutes, but it introduces a bit of noise, and the same applies to the others. So one thing that I normally do is I take these cases, and when I find this, one thing that we can do is, okay, let's get rid of this sort of shortcut or this inferred one. So if I say, whenever you find this pattern, this direct one, we can call this infer. So this is actually the one that's inferred that I don't really need, because if I have these two, the other one is redundant. So I can say, okay, delete inferred. Right?
Okay. Yep.
I can say, well, every time you find that, just do it. So if I run this, it's deleted 43 relationships. Not a big deal, but it's probably giving me a much cleaner graph, right? Without these elements, right? So if I rerun that, it should not find any case, right? Yep. So now we have all the chains clean and no where is it? This one here it's that's the one that's returning no records, no results, because now we've got rid of them. So yeah, perfect. So we have the Wikidata one. Now let's do exactly the same, but with the second one, which is the mesh ontology. I'm going to take from the Wikidata the credentials, because they're going to be useful, because this is the new one. And that's what I could have done a better job at cleaning my code a little bit, because I don't want to necessarily replicate that, but I'm going to do it. I'm being lazy here. Again, the structure is very similar, and I wanted to use RDF-lib again. Now, because sometimes the SPARQL endpoints might not be identical, and sometimes you might need to access them in different ways. I wanted to show a slight variation. It's pretty much the same, but in this case, I'm using the requests which I'm gonna need to import. Oh, that's not. I'm not finding a pip. Did I not? So we have, I don't have my active environment. Oh, hang on a second. I believed I had installed it, because I need to activate my environment, right? Hang on a second, because otherwise it's going to complain. But I was going to say that here I'm using the request, just an HTTP request, which is very similar to what we did before. So this is my endpoint. This is my SPARQL query. In this case, I'm hitting, instead of the Wikidata, the mesh SPARQL endpoint. So you have something like this. It looks slightly different, but you can write your query here, and that's pretty much what I'm going to do, just for the test. So I'm going to take my SPARQL, which pretty much does the same thing we did before. So we take all the subcategories. This doesn't do the nice highlighting, so it's harder to read, but it's the same. So I'm going to limit this to 5 like we did before. And if I submit my query, I should get the triples pretty much in the same way that we did with the previous example, right? Okay, so we just wanted to run the same query, except that now we use a post request. In this case, I believe that's what we're doing. Get
Did we lose Jesus? I think so. Maybe. I think we, yeah, as you said in the beginning, his network is not. Oh, here we go. I think you're back. We lost you for a second, but you're back. You're back now.
I'm sorry. I was saying that the serialization format that I'm selecting is turtle, and the rest is identical. So the same authentication. I create my config with RDF-lib neo4j, and the only difference is that instead of being the output going through a graph, I pass the result of my request as the input to my Aura ingestion, and that should be pretty much the same. I wonder if I need to activate my. Give me 1 second. So I think I have to do. We need to activate. Good. And I have, yeah, that's what I was hoping. I have RDF-lib, and now I'm going to need a request. And hopefully that will bring that, and I can now safely run my code. And this should do something similar to what we saw before. Connects to the store, to our Neo4j Aura instance. it should be writing the triples and hopefully get back in not very long. But let me get back to our Aura instance. We start seeing mesh diseases as well.
Yeah, this is probably a little larger than the other one, so it takes a little longer.
It probably is. So, but as it writes and it's batched, so we'll start seeing, we see mesh diseases here, which again, they're being taken let's reshape the order. These we get. That's pretty cool. So again, we have something similar, the label, the URI, and we can expand it. And we will have different things. So we will have, again, the usual taxonomy that we had before, but we start seeing same as relationships that, if you remember, were the ones that were connecting, in our case, the Wikidata disease to...
nice. Yeah, that's pretty cool.
And yeah, and you will see that there's a reasonable match in the name. So that's what we get out of that. So cool, things are linking nicely. This is still writing. I wonder if it's again my network issues. Sorry about that. But I will not stop there. I'll start looking at the third one. Like this, we move forward and we can start looking at the patterns. So the third one is the disease ontology. And like this, I wanted to try even a third approach to loading data using RDF-lib Neo4j. And this case is slightly different because the way in which the disease ontology is released and is delivered is through GitHub. So there's not even a...
okay.
Yeah, so if we go to disease ontology, you will go to this portal, and if you go to downloads, it will take you to GitHub, right? So you can go to the GitHub repository, and you will have the releases, and that's where you can get the different versions of the disease ontology. I'll go with the base one. But the main difference here is that we cannot hit like a SPARQL endpoint like we were doing before, but that's not a problem, because what we can do with RDF-lib is, okay, I parse all the triples in this ontology that I get from GitHub. I specify the serialization format, which is RDF XML. And when I have it in the graph, I can run queries against that graph in memory. So I'm kind of loading the ontology into my local graph in memory in RDF-lib, and then I run a SPARQL query pretty much in the same way. So instead of hitting an endpoint through HTTP or through whatever protocol, I load it locally and run my query. But then in the end, I get exactly the same. So I get a subgraph with my query, and then I load it to Aura. And I'm going to do the same trick. I'm going to copy the authentication. And with that, we should complete the picture. So that's the credentials. But ultimately, I do exactly the same. So I create the store pretty much like we did before, and that's pretty much it. So this is still writing. I mean, let me check how far has it got. That's unusual. Maybe it could be also. So actually, I'm going to.
Hasn't progressed much since I think it was just jumping up 50 or so nodes.
Oh, right, you're seeing it there, right? I was going to do a query in case there was.
Yeah, I think just before you refreshed, it was at 1800 something. Now it's in 1822.
Oh wow, 267. That sounds like it might have died, and that's very, very slow. So I wonder if that is unfortunately my network might be causing these issues, because the first one was lightning speed.
Yeah.
And
that was super quick.
Okay, let's try something. Maybe we're gonna make it all a lot worse, or maybe we are. I'm thinking of, why don't we try to run this one in parallel? So because I'm
what can possibly go wrong?
So many things, but let's do this anyway, because I'm conscious of time and I don't want to run over. But I wanted to show these kind of three approaches. it's kind of slightly different. So ultimately, the great thing is that the ingestion part is pretty identical. Oh, there's uniqueness constraint. Oh, it's found. I was confused because I thought it has not found, but it's saying that it is found, so it's all good. So yeah, I was saying that. What was I saying? I got distracted with these, but
the approach with the three different.
Oh yeah, the three different variations of whether you have a SPARQL endpoint that you can hit directly with RDF-lib, or a SPARQL endpoint that you can hit through a HTTP request, or no SPARQL endpoint, just a dump of the ontology that you can load into memory and import. Again, it's always with RDF-lib. This is getting a bit bad. So why don't I kill this and start again? So let's start with, let's do the disease ontology first. And let's see if it does any better. The good thing about this is that you can run it as many times as you like, because it's idempotent in the sense that it will not rewrite the graph. I mean, if there's new triples, there will be new elements added to the graph. But if you reload the same ontology and you had it already, it will be no changes to it. So hopefully this is writing the disease ontology. Well, we had to. So if we do something.
There it is.
So we have
at least they created a couple.
Disease. Oh, that's very, very, very slow. It's going to be an issue. One of these days, of course. That's
yeah, that's
well, that's not good. It's loading like seven triples per second, which is too bad. What can we do? Because I have my queries that start actually finding the misalignments between them, but of course they're going to give very poor results if we don't have
have enough. Yeah, that's true.
Well, that's strange. I mean, that might. I'm inclined to think that might be the either the disease ontology, not the mesh. Yeah, that's very, very slow. Let's try one of the queries, but it might be.
I mean, we can at least show in theory what you would be doing. I mean, I know that it's not exactly what.
Let's see if we're lucky, if we've found any triangles already. I had some pre-queries here, or maybe I can write it myself because it's not there. So a perfect triangle would be a pattern where we have all three linked together. So we would have the disease ontology, something like, let's call it, we don't even need to, the disease ontology, connected to a mesh class, and connected to a what was it? The Wikidata.
Yeah.
Now, and these ultimately link back to the original. Let's call it D and D here. So we have the disease ontology version connected. I mean, we could be specific because we called it the same as relationship, but basically we see the pattern, right? So,
yep.
So if we have these triangles, so this is let's call it trip, and I'm going to see if we, in case we have multiple. Well, we have some. So
nice. All right.
So we have some. It looks like the names match, which is to be expected, right? So
looks good. Yeah.
Yeah, the next thing that I was going to try, and probably will leave that to another session, is work on these descriptions. And the thing is, they're not always there. So it looks like the disease ontology has a rich description of the ontology of the class in this case. Giasus, whatever that is, it has a rich description there, because that would be a potential element to explore if we use back to vector search and using LLMs. If we vectorize this description, and we had a similar one in the other two ontologies, in the other classes in the ontologies, we could do a search and find similarities. I mean, in this case, we don't need because they are already declared to be kind of same as. But we could find for the ones that are not linked potential matches based on that, right? So we have Rocky Mountain spotted fever. There you go. So that's a good match. But then we could have something like an incomplete triangle, right? So we can have let's see if we how would we put it? So if we have a same as or a chain of, let's call it a chain of 2, right? And that doesn't close the triangle. So this will be the, let's call it the end, and then the we're not how would I put it? Maybe because if we do that, it's going to catch also the triangles, right? So am I right? So if so this is, let's call it incomplete. If we start, we don't need, it can be any resource. Yeah, this is catching. Oh, and that's interesting. I didn't know that existed. So we have same as relationships. So that's cross references. Oh, this is a resource. This is not. So this is ontology. Let's do the same trick as we did before. So we, how was it? So we have to reorder and put the disease ontology first. There we go. So that's better. So we have some external elements that have not been linked. I don't know if that's because it's in the process of importing it, but this might be, this is a mesh.
Maybe that was one of the one that have been not completed, or might be corrupted through the abortion.
Exactly, because if it was, it would have the mesh type. So maybe it's a broken reference. Maybe it's actually one thing we can do always is do that and find what it is. So it's a valid one, but maybe it's a remember how we were filtering and not importing the whole mesh. So maybe it's one of those that was excluded. So we have a reference to something, but we didn't import it. So maybe it was mentioned from the disease ontology. I don't know. That's one hypothesis, or it might be.
Maybe it was just not syncing all the fields because of the issues.
Yeah, the ingestion, because I killed the process halfway through it. But anyway, that's two.
But if you scroll out a little bit, I think there was another one that was clearly not completed.
This one here?
What was it? Yeah, here on the right hand side. Here we missed the wiki. Which one do we miss? No, here we missed the one. We have the disease, the ontology in the middle, and we have a relationship to the other two. And then there's
So that would be a good example, right? So this is clearly probably a missing, or maybe not. Oh,
no,
that's an interesting one. Yeah, exactly. So that's the, what's the hierarchy if it goes up like this? Okay, so this is one of the examples that I wanted to show. So we have a same as here at the bottom. We can ignore this one because this is one of these incomplete ones. But we have a match here.
Yep.
But then this has this parent. I wouldn't be surprised if these two happen to be linked, or there you go.
Perfect.
So that's nice. What I was expecting.
Yeah, good.
That's exactly the example that I was trying to describe before. So we can make these a bit bigger. And you see that there's a different in granularity, right? So here we have a same as at 2 different levels. Let's make these go away. And the same as here, this is the disease ontology. And no, this is the Wikidata, sorry. So we have a direct has parent between these two. Whereas, oh, no, that's the same as. That's, no, I'm mixing things. I thought it was a parent. So this was the middle one, and this was no. So it's similar kind of granularity, right? So no, that's not the kind of the case. What I was looking for is when we have additional levels, because this is in the ontology.
Okay. Yeah. So the bottom are the different ontologies, and
exactly. But I think that's the case that my magic query code here. Is that the one? Word count? No, that's not the one. I can probably write it quickly, but again, I don't know if we'll pick up one of those because because of the incomplete ontology. That's unfortunate. That's a bad one. But I can yeah. Let's try to. I think I have an older version of this that would pick these sort of different levels of granularity. Give me just 1 second.
But I guess we can also imagine what it would be, you know, if you had these three. And now we have these three ontologies, and we have different levels, where one is more detailed as is the other. Oh yeah, okay, you've got it. Because otherwise, I think we could probably discuss a little bit what you would do about it if you had that kind of scenario.
Yeah, let's see what I was trying to do here. So I'm finding that like the same thing, the top match and the bottom match, right? So we have we got the top link and the bottom link. I'm matching disease ontology with mesh ontology, and then I try to find. I think let's run to see if we have some examples. No, damn it. It's what about between the disease ontology and the Wikidata one? Unlucky. So what about the other combination? Yeah, that's some mesh disease. Well,
okay.
There you go. Found one.
Good.
Let's take the simple one down here. Perfect. So yeah, here we go. So we have a same as at the bottom level, same as at the top level, and then yeah, we have a different level of granularity. So we have an intermediate class here. So that would be, how can I make it a bit bigger so that it's nicer to read? Can I make it a bigger one?
No, I think it's fine. I mean, at least.
But so that the thing is readable. Yeah. But we see that we have and in this case it would be the same, so that we can read the whole thing. So yeah, we have a match here, and there's an intermediate category that's defining one of the ontologies and not the other. So what does that mean? I mean, does that mean that this ontology, the Wikidata one, is probably less rich and maybe could be extended with this additional one? Well, that's to the interpretation of the expert. But the great thing is that we can find these sort of patterns of misalignment that are bound by these two kind of matches at the top and at the bottom. So this is the same that we're seeing in these other ones. It might be a bit more confusing, but we have at the bottom the same as, and I mean, putting an sort of an inverted order, but the idea is the same, right? So we could even hide some elements, but you see how we have two examples of these here, right? I don't know how to put it in a way that's readable, but you see how, you know, in this case we have a match with two classes, right? This intermediate one again, and for these other one we have again a multiple set of categories inside. So yeah, I think, you know, clearly the data ingestion problem is complicating our lives.
Yeah, unfortunately, bit unlucky today.
Yeah, we had to have one of them. It was meant to happen. But I hope at least the important part, and I'll share the queries that in this case were not returning results, but should. And the important thing is how we can, you know, bring the different ontologies together into a single graph with the RDF Neo4j with you know, just a couple of lines of code. The complication in a way was in the SPARQL part, where you have to know how to extract the bits of information that are useful to you. But having the three graphs or the n graphs in Neo4j make it possible for you to then play around with these shapes and find, you know, the different levels of granularity, the incomplete triangles, and there might be many others. But that's where you can combine the different patterns. And ultimately, the idea, if things had worked nicely, would have been to go and vectorize the descriptions. Remember how we could use that and have an additional comparison point to align them.
Yeah.
But anyway,
yeah, and I guess then you all do this for a purpose, right? I mean, you want eventually have an ontology or a knowledge base, knowledge graph that you will then tie with your own data, and then you can see, okay, I have from all these validated resources, I have entities and I have definitions, and then I put my own data to it, and I can map it accordingly and can say, okay, fit that fits here. That is a slot direct match. Maybe your ontology or your internal data is even more granular than these. You can add layers in between, but ideally you kind of like match and say, okay, my internal documents, my internal resources are mapped then towards these ontologies, and then you can see, okay, where are the relationships, and then you can have that additional information and then use that for queries, for applications, and use that very rich knowledge graph that you then have to find these links and to connect things from your knowledge towards other data sources where you can say, okay, is this apparent? Is this a relationship between disease? Is there some similarity here? And combine the outside knowledge, I would say, the global knowledge on the field with your internal data.
Yeah, because very often these ontologies, they're used to annotate sources. So you have an article or a scientific paper, and there's a mention of a particular disease. And in order to have this precision, you kind of annotate it with the ontology. And like this, you enable kind of semantic search, and you can connect the dots. But that's so there's two angles. I mean, you can manage the ontologies themselves and find, hey, two teams or two organizations have worked on modeling the same space, and there's misalignments. What does that mean? I mean, does it make sense to reconcile those? But sometimes it might be a question of making more consistent use and access to data that's annotated according to those, so that there's different ways to get value from it. So yeah, it's not the greatest show today, but at least hopefully the code will be useful, because ultimately one of the things that we want, and I mentioned at the beginning, is if people try this RDF libneo4j library, there are 3 examples on depending on what your data source looks like, how you can use it, and there's some more even in the documentation. But let us know how what you find missing, and I'm sure the team will be more than happy to take that input as a to drive future additions to the library.
Yeah, no, absolutely. Let us know. I think we kind of answered your question, Alex. I hope with the insights and the analysis that these techniques would open up for a researcher.
Question on the index on Wikidata.
In the chat, yeah.
Yeah, so I mean, the good thing about the I didn't have to add specific indexes, because the only one that we need is we add an index on resources, which is we know that resources basically is the node that encapsulates URIs, and URIs are unique.
Yep.
But that's the only universal kind of index that we need when we import RDF data. So that should not. I have the impression that it's been a network issue, because what makes me suspicious is the first one
went to
the second to import thousands of triples, and then the other one was kind of so yeah, sorry about that.
Unfortunate. And then the other question from earlier from Samuel, and I guess it's more like a wish than a question, but I can I can understand where it comes from. Samuel says, I would really like to see an ontology standard represented only by graphs with definitions of rules and constraints without having to look at the strange RDF standard.
Yeah, well, in a way, you don't. Yeah, you shouldn't need to, because the RDF is the mechanism to exchange data. So you should. I mean, even for we've used Web Protege and Protege many times here, so you don't really have to necessarily see the RDF. So you probably will have some tools, some UI that will help you creating ontologies and taxonomies and things. And then, yes, there is this serialization format that we use as the kind of the vehicle in a way to move data from one place to the other. But I can understand that writing RDF is not everyone's cup of tea, and shouldn't be.
I totally understand it as well. The good thing is you have to set this up more or less once, and then once this kind of like works, you have your ontology set up, you have your graph base, and then you can just move on.
Yeah, totally.
All right, we are a little bit over time. I just wanted to make sure that you know what's happening in the next few days. So on Monday, the 26th of May, so next week, Michael and I will talk a little bit about Discover Neo4j Aura. I think Jesus presented it today a little bit that what that their graph database as a service offering we have, and we dive into a little bit more of the features and the new additions to the user experience from that angle. So if you are an Aura user or looking at using Aura, then it might be an interesting session. It's very concise, quick dive into a feature, and then we are done. The call for papers for nodes is still running until the 15th of June, so you have a couple more days. So if you are inspired by our series here or by something else around graph, and you want to share it with the wider world, then we encourage you to submit a session. It's really fun. It's all online, so you don't have to travel anywhere. You can do it from your own living room or office, basically. And yeah, it's a great event. So really encourage everybody to be part of this. And yeah, if you have further questions, if you want to know what's next and what to do around Neo4j, there is Graph Academy. We have knowledge graph training courses there as well. So if it is interesting, maybe it's an idea to what we just showed today, converting RDF ontologies into a Neo4j property label graph. Maybe that could be a Graph Academy course at some point. Aura free as well, and community and more on the developer pages. You find lots of resources around basically everything: drivers, GenAI, application development, and that's on our developer pages, and there are the docs as well. What time the Aura presentation is on 5 p.m. Central European time, so same slot time-wise as this session here, 5 to 6 Central, 4 to 5 British, and I'm sorry I cannot convert it to any other time zone. But it's the same. It's the same as going meta, basically. Yeah. All right. Cool. Thank you all for watching. Again, thank you, Jesus. Sorry if we had a little issue technically with the network today, but the code and all the examples, as usual, will be up in the repo, so you can just do it yourself and have probably more luck with the import, and then you can play around a little bit with the ontologies and see how it was supposed to work instead of
exactly
today. Okay.
That was it.
That was it. Thank you very much.
Well, see you soon, because I think since we delayed this one, we're gonna have the next one.
Oh yes, yeah, exactly. We will. Yeah, I think I should have opened with that, but yeah, good reminder. Thank you, Jesus. So we delayed this one to end of May. We will therefore skip June, and then we will be back in July, early July at the more or less usual slot, 2nd of July, with the next Going Meta episode. So yeah, stay tuned. We'll announce it as soon as possible, and yeah, don't be worried if we are not posting a Going Meta in
We're not gone.
We're not gone, exactly.